Hello and welcome to Network Freestyle. I'm Darren Fulwell
And I'm Malcolm Budden.
and we are the Network Freestylers. Today's episode, as you can see on the screen, is Freestyle 107 and we're going to have a look at how to go about building a data center. Now, fairly standard network approach, but what we wanted to do was talk about the experiences that we've had of mapping business requirements to the network architecture. So we're not talking vendor specifics, we're not talking particular features that you might find or want to use. We're talking about the building blocks of how we put together a data center architecture. Now, Malcolm, you've had some recent experiences with this one, so you're going to sort of lead us through this, hopefully. Do you want to start walking us through the process?
Sure. Yeah, so just to add a bit more context around it, pretty much most of the data centers that I've worked on over the years have had a very common, design as to how they actually look. As you mentioned, Darren, you have different requirements that come in from the business, but that's more around, to me, it can drive, the actual architecture to an extent because you might have constraints around cost or, I don't know, like delivery of specific infrastructure in the ground in a region. So, for example, if a customer wants diverse links between their data center, they might have diverse links to an extent, but there may be a pinch point because in order to get the diverse links, they might have to pay hundreds of thousands of pounds, dollars, euros, whatever currency is in the local region. So, but like just taking it back to the start, as we always talk about, people don't just design data centers for the sake of it. There's always a driver, and that can be things such as, but not limited to, a natural technology refresh, which is normally around 5 years, 5 to 7 years, in my experience, that an organisation will have a data centre running. It could be a merger, it could be an acquisition, it could just be additional functionality. It could be that somebody has a huge budget and deep pockets and they want the latest technology to play with.
And never happened to me.
Exactly. It could be, it could be as a result of an unexpected scenario. So, for example, there might be, let's think about something a bit more modern, software-defined data center. I've heard of very big customers, not that I've dealt with, but through people that I know, who have, for example, taken a small spine leaf pod of a SDDC, so software-defined data center solution. They've put it on in a part of their environment which is low impact, and it's applications which are, all applications are important, but low priority applications in the wider scale of things. And they've loved it so much that they've then spent millions on deploying it globally. So there's lots of different things that can drive a data center refresh. Normally it's, the business evolves, and especially now, I think we're seeing, you work in the integrator space, so you probably see it more than myself, but that curve is starting to come where it's like traditional, like core distribution access in the campus and then core distribution access in the DC, is more moving towards routed access in the campus, which we're not really talking about today. Routed core distribution access, and then the software-defined overlays in the campus, and in the DC, more of a spine leaf cloth architecture, running, overlays, software-defined orchestrated data center networks to support things like microservices, east-west traffic flows with segmentation, etc., etc. So I think a bit of a transition at the moment, where that last part that I mentioned is really starting to gain some traction. However, in general terms, I think that there's still been that spine leaf architecture for a few years, but now we're starting to see, adoption of like a bit more advanced deployment of the features that can operate on top.
So, but I mean, fundamentally, what we're talking about here is these great new options for to allow us to do stuff. You've talked about the sort of there's the micro segmentation and the microservices and the containerized applications and all the rest of it. It's that fact that applications have kind of changed, right? They don't look the way they used to. There are requirements that they have on the network infrastructure to function. And you fail over and go production DR, and you've got that whole active versus active standby type question. All of those things are the key parts, really, I suppose, to set the requirements for what that data center needs to provide, right?
Yeah, and I think that it needs to. I think one of the key things from that is that things are getting more complicated. They're not getting easier. They might appear to be easier to manage because we're getting a lot of good tools coming out in the industry. We're getting automation and orchestration tools. So it's not really around like plumbing VLANs around fairly complex environments anymore with an engineer. Well, it is sometimes, but that will go away. But under the hood, it's very complicated, and that even though that's hidden to an extent, you still really need to have a solid underlay. I don't mean that in the literal terms with the underlay. I mean like underlying infrastructure needs to be.
So the underpinnings of the whole environment, right? Yeah.
Basically everything that's in your design principle block. So it's like scalability, availability, security, all that kind of thing. It really, in order to provide a good foundation for something as complicated as a data center, which you'll see the diagram that we're about to draw out is going to get quite busy. And it's based on like a normal data center, but when you start layering the application, the features to support things like the application containers and being able to basically switch environments on and then switch them off, tear them down, move them, make them available across multi-sites. That really needs to be quite a simple, solid, traditional underlying infrastructure, but what you put on top, and predictable as well, but what you put on top is where the magic kind of happens. So we're really talking about that base infrastructure today, and in maybe further episodes we can talk about different software defined and fancier things like ACI and Cumulus and things like that. Yeah,
I suppose, and this is where the experience comes in, right? That while if you listen to all the podcasts and all the news and everything, it's all talk about containerized applications and Kubernetes and all the rest of it. There are a lot of data centers that just aren't like that. They run virtual machines the way we always did. They run Windows and traditional operating systems and VMware and all of those kinds of traditional environments that don't necessarily map to the more advanced and more modern software-defined environments, right? So it's key to understand what the requirement actually is from the customer and to understand where they are now and where they're trying to get to before you even start this.
Yeah. So the agenda on the screen then, so when I'm talking about requirements, I think we've covered some of that already. Like the requirements can vary greatly. I'm not going to talk about one specific customer or anything like that because, as I say, I would approach most data center designs with the same architecture in my head and then tailor it to a customer specific requirements. If they said I've not got enough money to do that or whatever, so we'll talk about some requirements which might drive the architecture as we go through. So point one is going to be like a continuous conversation. We're going to I've just basically split out what are typical building blocks in a data center. So the core infrastructure which links typically 2 sites in most enterprises together with a data center interconnect, and how the routing design looks within each data center and between. The internet perimeter would be, like your firewall infrastructure at the edge, DMZs, what sort of services you would run within the DMZ, and we typically refer to that as the untrusted zone, or that's what we're using as a terminology for this particular discussion. We then have like the WAN zone, so some customers might have a single MPLS link in their data center. Some customers might have an MPLS link, a VPLS link, an internet link, a 4G link to take multiple feeds, and there's different ways to deliver the WAN connectivity. So we'll talk a bit about that in the semi-trusted zone, and we'll try to highlight these as we go through. And then there's a DC hosting zone, which is where your applications are going to be hosted and accessed from the campus. And then the security architecture, we're really talking about, how we, that's probably overlaps with point 3. So we might not need to talk about that, and we'll talk about the security through it. So
yeah, I think like you say, a lot of this stuff interlinks, haven't you? But you've got those three primary zones, I suppose, but the other stuff, requirements for all of those, the security elements of all of those. So it makes sense.
Yeah. So a customer comes to you and they say, "Hey Darren, need you to build me a new data center." So what do you ask them? What do you ask them? Right. So let's say they've got 2 data centers. They've all you know about at the moment is they have 2 data centers, and they have to get to the internet, and the WAN. How would you engage that conversation with the customer?
Well, I mean, straight away, that's basically turning around and saying, right, you've got a number of services or applications that you want to deliver to users who live out in the internet. You've also got the question of how you want users on the outside to get access to those services, whether that's a VPN or whatever. Then you've got the question of your users who are based within your network, within your remote sites, who are accessing applications across the WAN. So how they get to those, and then it's how those applications want to behave and perform in terms of failover and DR and that kind of thing, right? So that's kind of where I'd start the conversation, I guess.
Yeah, exactly. So I'm just wondering, do we build data center out to the perimeter, or do we build perimeter into the data center? Let's start perimeter into the data center. Right? Well, actually, no. It makes more sense to define our data centers and then build out.
Okay.
First of all, typically within a data center, you still have the basic concept of some of the traditional stuff. So you're going to have like core data center switches, which can either double up as collapsed core, where they can service inter-site connectivity as a dedicated device, or they could be like a spine in a spine leaf scenario, which then can also interconnect the 2 sites. So starting off from the basic perspective, everything that we're going to draw on this, because data centers are critical, everything that we're going to draw, unless there's a few exceptions, is going to be redundant, because it doesn't make sense to design a new data center without it being redundant. So if we say over here is DC1, and then over here is DC2, and within DC1 and DC2 we have core switch 1, core switch 2, and data center 2 we have core switch 1 and core switch 2. Now, dual connected, whatever. So where do we want to go next, right? So within each data center, we're also going to have like some application servers, right? So over here, what we're going to draw, sorry about that. Over here, what we're going to draw is, oops, that's terrible. I need to change the size of that. What we're going to have is some application servers. So if we have a couple of application servers here, and a couple of application servers up here. Actually, that didn't go as planned. We have 2 application servers here. Which are connected to nothing at the moment. So what does an application server need to get onto the data center network? It needs connectivity to the network, right? So we're talking about the Ethernet network. So let's draw in a couple of top of rack switches, and this is obviously a very small representation of the overall data center. I've missed a couple of bits. So let's just draw one more component here first, which we'll come back to in a minute before I forget. So we've got a couple of top of rack switches. Forget those things that I just drawn for a second. This is a top of rack switch. Top of rack switch. And these will be connected. So what we're just let me back up for a second. So what we're talking about here is basically 2 core switches which are going to be interconnecting the 2 sites via, let's just say, 10 gig or 40 gig DWDM fiber. So the C1 and the C2 via the boxes that sit to the to the right and to the left of these devices will connect the 2 data centers. Within the actual data center, we will be using the same core switch to connect to the top of rack switches, where the top of rack switches are then used to connect the servers. So let me just draw in a red line is like the fiber link between the top of rack switches and the data center, the core switches. So top of rack switch 1 will get a connection to core 1, and top of rack 1 will get a connection to core 2 as a redundant link as a minimum. And then top of rack 2 will have the same, and the same in the other data center. And you'll see here we're basically building like a spine leaf scenario where the spine is the core 1 and core 2, and the leaf is the top of rack switch.
Cool. So that's basically in each rack then, where there are servers located, what you've got is an access network, I guess, a presence there to minimize all the cabling throughout the environment by providing connections to those servers locally within each rack, right? Okay.
And how just touching on like some basic theory about the spine leaf scenario before we go any further, and I'll score this out. Why spine and leaf is so scalable is because if you need, let's say you have like 100 more servers that come into the data center environment, and these top of rack switches don't suffice, then you can add like more top of rack switches like this, and so on. You get the idea, right?
Yeah.
So I'm just going to, for the sake of space, I'm just going to take that out, and then you basically connect your servers to those top of rack switches. If you then get to some sort of scaling issue where you run out of ports on the core or the spine. What you can then do is add more spines and then add more leaves. Wrong color, but you get the picture. So then your scenario is like this. You're connected to every one of the cores like that.
So that's really a kind of a bandwidth thing, right? Where if you need bandwidth between those top of rack switches, you add more spines, so you've got more paths from between the top of rack switches, right? So
Yeah.
it gives you that greater bandwidth. Yeah. Okay.
Yeah. So when I was talking about scale there, that would be like scaling the bandwidth up. Yeah.
Yeah. Of the data center fabric, right? Understood.
And if you need to scale the number of top of rack switches, that's where you have to really consider. If you let's just say had a Nexus 7702, for example, as a spine, then you're always going to be constrained by give or take 48 ports per spine. So you need to plan. And then if you're running multiple VDCs, for example, sorry, I'd say that I wouldn't go too much into features, but it's just to use as an example, like if you start using multiple VDCs, you start burning ports by having, VPC peer links between VDCs and things like that, depending on like your architecture. But if that was a Nexus 9K or ACI type spine leaf situation, then you would basically need to size these spines to accommodate what you felt was going to be the maximum number of top of rack switches and uplinks that you would need to accommodate for now and in the future.
And I suppose you've got that option of kind of a tiered spine leaf if you go down that path, or the spine leaf architecture in itself lends itself to swapping out those spines, I guess, for larger ones along the way without impacting traffic paths anyway, right? Because you can take one out, you can replace it with a bigger one, and drop down through the topology to do that. This comes back to the last show we did, right? I'm talking about scalability and understanding what the requirement is to scale the environment out, and making the design choices that allow you to scale in the way that you need to scale. So
yeah. And I mean, like one of the other things that's worth mentioning, but not going out and how do you get outside? So if you think like your servers are basically sitting at a dead end here, because they basically at this point, because you're not drawing anything else in, we've not connected the spines or the leaves to anything. Basically, if this is the rest of the network, you basically connect your spines to the rest of the network, or your leaf or leafs, which you call like a border leaf, and that's the ingress egress to the the server infrastructure and a more modern spine leaf scenario. But
I was just going to say that's dependent on, I guess, on the technology then, right? Because some back in the day, certain topologies allowed you to connect the spines to things, and some technologies don't allow you. It has to be done through the leaves, right? So it can work either way, can't it?
Yeah, I mean, I think traditionally, like what you're going to be doing in a legacy scenario, and how this topology will look, is you would be coming in via the spine switches, which basically equate to the core in the core distribution access model.
I think so. Just from reference there, I think it depends on what you're running over that topology, doesn't it? Because if you're running an overlay network, typically the leaves are the point where any encapsulation is done and any policy is defined in that sort of software defined overlay sort of architecture. So in order to break out of that, you need to pass through a leaf in order to route into the wider network. So it depends what the wider network requirement is. and B, it depends on whether you're using an overlay technology or not, and what that overlay technology is. So a few things there that it's dependent on, I guess.
Definitely, and again, I won't labour the point, but yeah, you're 100% right. I mean, traditionally, this spine leaf in the new world of like SDN and in particular, if we talk about Cisco ACI, in order to get in and out of that server farm infrastructure, you would typically come in via, the border leaf, which I drew there, as opposed to, not that. You would come in this way. Via the border leaf, and then you would go up to the spine and then potentially through a firewall before you even go up to the server farm. So that was that's basically how the traffic flows typically worked. There is enhancements if we're talking purely ACI where you can actually come in via like the spine using Cisco EVPN and using something called Golf, but we're not. That is a real thing. I didn't believe it when I first heard the acronym, but yeah, it's definitely a real thing. So we can talk. We could probably do a session just on like ACI Golf, which effectively it's BGP EVPN in and out of the fabric from the spine, rather than via the border leaf. So yeah, it's a very interesting topic, and yeah, I actually quite like it. So
yeah, well, definitely one for another day. But yeah, I think you're right. I think it. So basically, it depends, right?
Yeah. So let's. Why did I draw two servers here? Right. So the reason that I drew two servers here, if we just say, right, well, how do we connect the servers? So if we just say like, 10 gig links, this one has a server to top rack switch. A link to server. Sorry, it's late. This server has a link to top rack switch 1 and top rack switch 2. But I've had scenarios where some servers connect to top rack switch 1 or whatever, and other servers, for whatever reason, which I can't think of just now, it's normally just because of port capacity, will connect directly to the core. Or it could be something like, it might not be a server, it might be like a firewall, and a firewall doesn't, like, if it, again, so many products on the market, but this topology that we're drawing out, the spine leaf topology, it could work with ACI, it could work with like just routed topology between Nexus 9Ks, it could be a Nexus 7K or 5K to a fabric extender, and that's like a scenario where fabric extenders don't always work well with everything in the data center. So in those scenarios, so for example, if you need something with 100 meg port or something, let's say there was some kind of port constraint on the FEX that you had. Let's say you only had like 10 gig FEXs because the majority of stuff was 10 gig, but you had like a 1 gig, you only had like a handful of 1 gig devices. You would maybe connect this server 2 in the bottom to directly into the spine, which would be like, for example, the Nexus 7K in the data center. So yeah.
I suppose the other example is where you've got services like, say, firewalls and things like that, which need to be at a point in the network where they're part of the aggregation layer, I suppose, of the traffic. So yeah, understood.
Yeah, and like with running things like FEXs, like they're basically like line cards, but on the end of a fiber. So if you think back to the 60s, the way that I always used to explain how a FEX operated to customers is, although it's like a separate device, so a fabric extender is basically a 1U switch. That's what it looks like. You connect it to a Nexus parent switch, like a 5K, 7K, 9K, whatever, and it's the equivalent to like getting a 6500 chassis and slotting a line card into it. That line card will use the backplane within the chassis in order to send packets between different line cards. With a fabric extender, it does the same thing, but it goes up and down a 10 gig or a 40 gig cable in order to achieve it. Whereas if you actually put, like, for example, a 9K as the spine and a 9K as the leaf, then the layer 2 and it doesn't go up the back plane. It's contained to the local area, and that can improve traffic efficiency and various other things. So
again, it comes back to that requirement, doesn't it, of what servers need to talk to which other servers, and how much virtualization you've got going on, and all of that kind of good stuff. The volume of east-west traffic is a key part of that one, isn't it?
Yeah. So if we take this a step further then, and so now we've got our servers connected, and these could be like blade centers, they could be rack mount servers, they could be whatever. Well, that's your main option. So like blade centers, or like rack mount servers, or like a Hyperflex or VxRail or a Tanix environment or whatever. Typically, you've still got, like in my experience in recent years, you've still got some kind of like off server storage, so network based storage. So in order to talk to network based storage, you're going to need SAN switches. That didn't work very well. Yeah, you need SAN switches. So if I just draw these in, if my machine doesn't die. No, it's back.
Yeah, there we go.
Yeah, bit of lag, not sure what that is. Anyway, try again. So if we draw in, so I'm not as good with drawing the icons, but these are SAN switches, right?
Sure.
Now,
this is where we're using like Fibre Channel based storage, right, rather than Ethernet based storage or IP based. Yeah, okay.
Yeah, let's make an assumption for this video and this freestyle that this is Fibre Channel, native Fibre Channel, FCOE Fibre Channel, and that could be a constraint. So a requirement, it is a business requirement, right? Because it could be that like there's some sort of like I've actually looked at this before, where the challenge, which we'll get onto in a minute, was the interconnect between the two data centers. So the customer was looking at various different providers that could provide like Fibre Channel circuits between the sites. And we'll talk about that in a minute. And the reason for that was because that historically they had always used Fibre Channel as a storage.
This is always the thing, isn't it? There's always legacy. There's always stuff that you have to cope with that's gone before. So yeah. Yeah.
So we need to talk to so in these scenarios, you have to talk to like storage vendors, and this is where I say it all the time, like networks cannot be designed correctly unless you liaise with application teams, server teams, storage teams, as well as the business. So the business drive what they say, this is our business requirement, and then the IT department will say, or the IT partner will say, well, in order to do that, you need to use this type of application in order to deliver that functionality to drive revenue for your business. The application then has to run on a server. The server has like storage requirements, and and network requirements. In order to get on the network, they'll say, we need this much bandwidth. We need this much, latency, etc. So that's from the traditional networking, but we also need storage. So and that might be iSCSI. So that's a network administrator's dream. They're like, yeah, fine, IP based, we'll just route between the sites. We've got 40 gig between whatever, no issues. We'll put QoS on it, fine. But when you have things like Fibre Channel, if the company has had Fibre Channel for a large number of years, I'm by no means a storage expert, but when I've had these conversations, when you say something like, well, if you're using Fibre Channel at the moment, can you not just use iSCSI? It's like, no, we have to re-architect, redesign, completely redo, you know, a lot of work involved in like changing storage protocols. So it kind of comes down to like, what can you do from the network perspective, where we find ourselves in that position more often than not, rightly or wrongly, you know, trying to accommodate these types of requirements. So yeah, that's some sort of background as to why, you know, you might need to think about the part that we're going to talk about next. So, you have anything further to add?
No,
Yeah.
no. I mean, it's you're spot on there. I mean, it's that thing of always having to accommodate. Like I say, nothing's ever greenfield, right? So there's always been a legacy of some sort, and whether you have to build a method of migrating from that previous legacy environment, or whether you have to actually integrate it, then that's got to be part of the design. That has to be part of the process. You have to be able to do that. And like I say, the storage is always a thorny one, because traditionally storage was big, expensive, you know, and a long-term purchase. So
Yeah, so as we're talking about a bit of a technical hitch there, so hopefully it's not too bad. But yeah, we were talking about like some of the drivers for Fibre Channel might be like historical, for example. So for the storage team to like change from like historical Fibre Channel type storage and move to like an iSCSI environment, which would be like IP based. When I've had those conversations, they've just been like, you know, an absolute no go. So yeah,
it's a painful thing. I mean, hey, we know how difficult it is to migrate from one networking technology to another. It's the same question of you're asking of the poor storage guys, right? So yeah, no, it's a tricky one. I mean, it's interesting because obviously the requirements on the storage as well. I mean, you're about to draw some stuff out here about how the storage is connected up, but of course you've got to worry about replication and synchronization between the DCs and that sort of stuff, right? So
yeah,
and all of those things are affected by the technologies that you use to deploy them. So you mentioned before that we have to talk to everybody who's delivering stuff in the data center. Well, that's everyone has to talk to everyone. It's you know, when you're delivering a data center environment, you're not delivering a network, you're not delivering storage, you're not delivering compute, you're delivering all of those things as a whole system, right? So
yeah. So absolutely. So I mean, like going, let's just say like these things are Fibre Channel switches, right? And I've drawn two links in there, but you know, it might actually be that you only have one link, but more often than not, we're going with a redundant design, so we'll just assume that the storage guys can accommodate a redundant design.
yeah, I
Right?
mean, and that's you do the sort of multi-pathing thing over separate fabrics, don't you? So each server has a connection to the two Fibre Channel fabrics in this case. So yeah, that's pretty standard design, I'd have said.
Yeah, all good. Sorry, just I won't cut this bit out. I just need to stop the autofocus on my camera because I'm jumping about. So yeah, so we now have like what we have is we have core switches. We have two data centers. We have a core switching environment, which is prepped and ready to connect the two data centers. Also connected to that core, we have top of rack switches to form the spine and leaf scenario that we talked about at the start of the session, and that's the CLOS architecture. We have servers connected to the top of rack switches and over Ethernet. So the red lines are 10 gig Ethernet or 40 gig Ethernet, but more likely to be 10 gig or 1 gig, depending on you know what the device is. But more often than not, I typically see 10 gig uplinks from servers, etc. in the DC. Actually, like from the topper, like just to actually correct that slightly, between the topper, although I've got them in red, so between the topper rack switches and the leaf switches and the spine switches, things have probably moved on to where that's more typically going to be like 40 gig and moving towards 100 gig. So it's just probably when I done this design that I'm walking through, it was 10 gig, but it's normally like uplinks between spine and leaf is more likely to be 40 gig, and it's only not really 100 gig at the moment because the modules and the cards and all that are still, you know, pretty expensive, and 100 gigs probably overkill at the moment for some environments. It's not for others, but anyway. So we have the servers connected to the top of rack switches, and the top of rack switches connected to this, which are leafs, connected to the spine switches, which also operate as the data center core. On DC1, we have Fibre Channel, native Fibre Channel NICs within the servers, which connect to the FC, the green FC devices, which are within the blue drawn switches, which are Fibre Channel SAN switches. So they're dedicated for SAN connectivity, and then to complete, and then the same in DC2, we just have a mirror, and to complete this picture, we then have SAN, which is your SAN device, which are your Fibre Channel storage drives, etc.
Yeah, I guess they'll be cross-connected again to the switches, right?
Yeah, so they'll be like redundant like that. Now, you know, there's an argument for some legacy like equipment and designs and stuff like that you could like have that Fibre Channel. So, for example, we were having a chat about this the other day as to whether, you know, there's multiple different vendors like HP, Brocade, Cisco, all do like dedicated SAN switching. So Cisco would be the MDS, Brocade, and that they're really specialised in storage stuff. HP, obviously a big server vendor, but there's actually some switches that can, probably not just Cisco, but just because I'm familiar, and we were talking about this the other day, what is the use case these days of the Nexus 5K, because, or 5600, which I'm not sure if it's the 6K, but anyway, I've always known it as the Nexus 5K.
Yeah.
And that always had like the capability to license a small number of ports on so it's an Ethernet switch, but you might have like 8 ports or something that you can license for native Fibre Channel. So you can have like a converged Ethernet. So in that scenario, where you look here, the top of rack switch and the Fibre Channel switch, right and left of the servers, if you're looking at data center 1, could potentially be a converged switch.
Yeah.
Always comes back around to, like, you know, well, it comes to a few things actually. It's a little bit past just availability, because in this whole new DevOps world that we're moving towards, this might become a thing of a past. But, you know, traditionally, network team would manage the top of rack switches, and the server or the storage team would manage the Fibre Channel switches. So that's why I've never really seen like the converged Nexus 5K. Like, you know, I sold a lot of them, like when I used to work in pre-sales. They never ever really sold like the Fibre Channel licenses, because it was never the same team. And then you had the role-based access control was more hassle than it's worth, when they could just say, just go and buy a SAN switch and you can administer it. You know what you're doing. I know what I'm doing. Job done.
There are a couple of use cases in some of the validated designs, things like VBlock and a FlexPod and things like that, where they were actually used as part of that validated design. So you will have that where, for example, if you've got a Cisco UCS fabric connected up to a Nexus 5K at the top for Ethernet connectivity, but also the SAN storage is also connected to those same 5Ks to give you the connectivity through into the wider fabric. So yes, you're right. Typically, very not a common thing, but when you look at some of those designs that are pre-packaged and validated by cross vendor, it was something that was used quite widely. But we don't see it so much now, especially with hyperconverged being the way that people are looking at server infrastructure now. Less and less a thing, I think, is that sort of converged switch infrastructure.
Yeah. But yeah, as a historical thing, so like I mean, all these like historical things, we've done a couple of like other videos where it was like old hat technologies. I think always remember, you're never going to walk into like it's very often, especially the rate that technology is changing, it's going to be unlikely that you're going to just walk in and everything's going to be, unless a rollout is just finished of something brand new. But you're going to have to migrate away from these things, so sometimes it's worthwhile just dropping a few nuggets in there about that.
Absolutely. It's like you say, nothing's greenfield. So yeah.
So I think that kind of covers. Let me see if I can zoom out on this a little bit. That's better. So that kind of covers like so what we have now is like basically two islands of servers that are meant of server farms and services that basically can't talk to each other. They can talk within their own data center, but what we need to do is we need to be able to allow so if you've got a database server on one side that needs to talk to an application server, just making this up, and the other side, then it needs to be able to route. So it needs to be able to route out via the red line, hit the top of rack switch, hit the core, and then say, where do I go to be able to talk to this server? Or it could be a user. I'll draw in a campus LAN I might just do that now quickly. So I'll draw in a campus LAN. Campus LAN, basically, all I'm going to illustrate that as is a couple of switches. But this could actually be it might not be like this. This might be, for example, a dedicated data center with no campus LAN, right? So, but this is just to provide an example or one site could be one data center could like just be the main data center, but it could be a server room in an office building. So just to illustrate that there, that's like the campus LAN aggregation basically here.
Yeah.
And it puts another part of the picture together to say, like, if this is where the users are coming in from, and then it might need to route across to this data center for a specific on the right hand side, it might need to go to data center 2 for a specific service. So that's why we need IP routing capability between the two environments. But we'll talk about that, because we're linking them in via the wide area network as well in a second, or a few seconds. So let's talk about the data center interconnect. Right, so the data center interconnect, I'm not gonna get into like layer 2, layer 3. All I'm going to talk about is a very high concept level here. So we've got NTE. What does NTE stand for? It stands for network termination equipment. That's basically the box that the telco hands over the service to you. So I wouldn't normally in most network diagrams that won't even be pictured, but the reason that we've got it pictured is because we're going to show something that you may or may not be aware of. So let's say this is a bit of fibre. Give my PC a second. Keeps crashing out. Bit annoying. Bit of fibre.
Yeah.
right? And then within that fibre, all I'm going to do is draw a green line, poorly, but a green line and a red line. So first of all, let's talk very quickly about the red line. The red line is basically the Ethernet connectivity between the two sites. How that's going to look is if you've got like the core 1 and core 2 in each site, a round dot is a layer 3 interface, which I'm just drawing in on each of the cores. Self-explanatory. So you'd run something along the lines of like you'd run eBGP between data centers, and those would be your neighbor peering addresses. So you could do like neighbor on data center 1, you do like neighbor core 1 data center 2 IP address, and vice versa, and the same for core 2 to core 2. And that's normally, in my experience, just 2 eBGP sessions. You wouldn't be looking to like do like core 2 on DC2 to core 1 in DC1 or anything like that. I would just have 2 links over the red path. It's just a light path. It's called a DWDM wavelength for anybody who doesn't know, and we've selected to use one DWDM wavelength, which is a red one, for 10 gig or 40 gig Ethernet. Basically what that equates to is in this NTE device you have like basically one port which is like an SFP plus or a QSFP or whatever, where you just hand off that port to directly to the the Ethernet switch. And then by the same token, because we're running DWDM, which can basically, if you don't know what DWDM, it's what is it? Help me, Darren. Dense wave.
So dense wave division multiplexing.
Dense wave multiplexing. What that means in English is you can run up to 32 different services over a single piece of fibre.
Yeah. So each service is presented on a different wavelength of light, right, across the fibre. Yeah.
So one piece of fibre can do up to 32, but this NTE is what dictates whether you can do 32, because normally what you'll get on a point-to-point link between, unless you've got like a huge campus or something like that, if this is just 2 data centers, you'll get a 1U thing where you can maybe put 2, just like it's a modular like 1U unit or a 3U unit or whatever, and you put like a card in for like one port to have an SFP plus to hand over 10 gig, or a QSFP port to hand over 40 gig for the Ethernet. And then you would have another port like that, or module, which would deliver, you see the green wavelength that I've drawn in the fibre link, and what that basically will do is this. Sorry, that's incorrect. Should be the SAN switch.
I was just going to say, yeah, because it
Fibre channel switch. Bear with my laptop while it catches up. Let's try a different way. Yeah, that'll work. Sorry about that. The lag. Yeah, this will go this way to that fibre channel switch.
Yeah.
And this will go this way to that fibre channel switch. My laptop is not having fun today. But you get the idea. We're
so you're extending each of the obviously the 2 fibre channel SAM fabrics A and B in the 2 fibre channel switches. They're extending those A and B fabrics, I guess, between the two DCs over separate DWM channels, basically, right? So and that gives you your multi paths from the servers and the storage on the left to the servers and the storage on the in DC2 on the right. Yeah.
Yeah. And in some conversations where I've worked on solutions with customers, they were looking at like putting one dedicated link. So see the top link that's got 2 wavelengths on it. That would be like a dedicated Ethernet, and then the second link they were looking at, because they didn't know about DWDM. So this is like where consultants can have like uses, because they were going to go ahead with that and buy like or they said like they were getting costs, and they said, right, well, we get 2 dedicated Fibre Channel links and 2 dedicated Ethernet links, and that might be required for some, like for the diversity perspective, and if the SAN team and the network team are disjointed, so that kind of covers that.
Because again, it's looking at those design options, isn't it? Like say, you can have those as individual, as separate fibers, or you can use DWDM to converge those in a similar way, I suppose, to what we talked about with the Fibre Channel switches and the LAN switches. If you're using IP storage, those things are converged, or you can use a switch that will do like that unified fabric type approach, to reduce the number of boxes and reduce the number of physical cables, right?
Yeah, exactly. So right, so I'm going to try and whiz through the next, because that took a little bit of explaining with the technical issues as well. So
that's cool. So that basically what you've got there now is your storage and your server environments built out in the 2 DCs, able to communicate within themselves, to replicate and do all the cool stuff that they need to do to build clusters and whatever else within it. And I guess now what we need to consider is how that breaks out in order to present services to users, whether they're over the WAN or over the internet, right?
Yeah. So this is a firewall cluster in the interests of time, right? That's a firewall cluster. That's the back end firewall, if you like. We then have a front end firewall, same in the other DC. So let's just say this is like a couple of HA pairs, and then we might have like a switch stack here to provide a pair of switches. Or it could go like these switches. I'm just like, this isn't prescriptive. So what we have here, right, is basically a firewall front end, which is a perimeter. So that will host the DMZs, which we'll draw in a minute. And then the back end firewalls, which are close to the data center, which protect the data center. So traffic coming either from the WAN or the campus or whatever. Sometimes the campus is protected via the firewall, sometimes it isn't. So
you might have multiple security zones, I guess, as well in the within the data center itself, right? So if that firewall sits closely into the core, then you might have different zones of services. You might have, like, for example, PCI or GDPR requirements. That means that certain servers have to be separated from others with specific access wrapped around them. So I guess that's where you do that.
So then another technology glitch that we had to pause the video again, but I think we've sorted that out. So all good. Right, so let's get back to this and try and move on. Right, so we summarised the data centre there. The campus LAN might be on site, it might be off site. In this scenario, it's on site, and it would just route straight to the data centre. Even some people like to put a firewall between it. Some people don't care. Some organisations don't care. So again, that's a subject. But I mean, if you really want to put a firewall between it, what that basically looks like is you would need to have that like connected into a firewall and then a zone for the campus LAN.
I suppose as well, you could physically still cable it direct into the core switches and then just logically take it out to the firewall, right? Yeah, I mean, it doesn't
So
matter.
have it like that, and then that's a firewall pair,
Yeah.
and then you could VLAN it through, and
which again, if you're doing multiple zones in the trusted part of the network, you could use the same trunks, right? So yeah, it almost doesn't matter, does it?
So just zoom this out a bit. Right, so we're going to speed up a little bit. I'm going to redraw this a bit further up. So we've got iNet up the top. Now we've got like users, VPN, and then cloud services. Right, so what we have is like what we've drawn in is we've got two firewall layers. Still pretty common to have like dual firewalls. So you have like the internet perimeter, which looks after your DMZs, and then you have some sort of switching infrastructure. Again, the switches which are drawn in between in the firewalls, they could be dedicated like switch stack, or it could be similar to what we just described with the campus, where that it could all be plumbed into like this core layer and VLAN through, etc. So just for ease of like being able to understand the diagram, we've drawn them in as like a separate pair of switches. So let's just say that that's 10 gig uplinks. It would obviously be redundant uplinks, just like everything that we've got in the design. Now, and then the firewall connected redundantly there and there. So that's a firewall cluster. Now, the next layer up that we're going to build out shouldn't take too much explaining. So let's say we have like a WAN zone at the back end of the infrastructure. So that's a switch stack. And then we have like, keep the uplinks the same color. So we've got a WAN router, right, which is, it might be connected via, well, let's say like blue is like copper. Oh, in fact, it doesn't matter. Let's just make it red. It's uplinks, right? So this is basically like the WAN zone of the WAN zone.
Yeah.
And this might be like MPLS CE, which then probably need to draw this a bit further down now. So the diagram got a bit busy. So we have the corporate WAN and remote sites here. And this device connects into the corporate WAN. And we basically have the same thing over the other side of the network, where we have a router, a CE, a pair of switches. We have the connectivity. So these switches which are highlighted in blue, they're going to be like layer 2 switches, really. And we're going to route between, if I draw layer 3 interfaces, it's going to be between here and here. This might be a port channel or whatever on the firewall. Same at this side. So I don't know there's that much to say other than on the WAN side of things, other than some customers will go for like a single WAN router. It depends on the size, the size of the organization, what their criticality is. But if this was like an MPLS network, and let's say this was like, well, let's say that it was like 10 sites, 10 remote sites, or something like that, then the reason that the architecture could possibly look like this is because they might see is like having two CE routers in each data center as being overkill.
Yeah.
Not only from a redundancy perspective, but also complexity, because two separate routers is two separate routes that you need to control and make sure that you mitigate against the routing loops and things like that. So you wouldn't want you wouldn't want asymmetric routing or routes being advertised out of here, routes being advertised out of, let's use a different colour, out of here, and then ending up here and coming back down, and like doing some sort of like routing loop like that. Because if it's easy to control if you've only got a single point of entry into each DC, but if you've got multiple entries, that's where these problems can, in my experience, can kind of come up.
I mean, the other thing I suppose there is if you treat the two DCs as a single piece of network, I suppose there's no reason why you can't use that as a transit if you have a failure, right? So you lose, let's say the router in DC2 to get to services in DC2. There's nothing stopping you then passing traffic into DC1 and then across the DCI in order to get to those as a backup path.
Yeah, so that's typically, what I would see is like that traffic flow to come like that.
Yeah.
That would, it would be a two-way traffic. It would be in and out of DC1.
Yeah.
And that to me, like that in this particular scenario, that's, one design in particular that I had worked on that had this architecture. That was the rationale. Some customers don't really like routing like traffic like that between the data centers over the DCI, or they might say like, well, we'll use one of the DCI links for that purpose, but the other one has to be dedicated for like replication traffic or whatever, because we've got large volumes of traffic which are going between the sites. But that is the exact rationale, what you mentioned there, where instead of having like two CE routers, they would have like one CE router going into the WAN environment, i.e. the MPLS, and then they would leverage the data center interconnect because it's only going to be used for the amount of time that the WAN circuit or the router is down, right? So
Yeah.
it's not like they're looking for it. If you were looking, that was the other way that I would say that you would want a second router in this data center here. Well, it doesn't matter about the color, but a second router into this data center is if you had like a service down here that you needed, or a couple of services that you needed that one to go that way and that one to go that way. So if you were doing some kind of load sharing into the same DC, then that might be a valid scenario that would drive having two routers and two WAN links in one DC.
And so this comes back to the requirement of the application, right? So this is saying, right, we need this application to be delivered in this way, therefore that drives the network design. Similarly, the active standby thing, right? Because when you're bringing WAN traffic in through a firewall to get to the DC, you've got to worry about symmetry of traffic flows. And so you've got to say, right, okay, do I have a primary path that always forces traffic to go through the firewall in DC1 to get to the WAN? And then only if there's a failure in that path does traffic then move across to DC2? Or do I have to come up with a mechanism using, I don't know, natting or source natting or something that allows me to use both paths because, again, of the availability of the services? So the mechanics of the failover of the applications is important, isn't it, to the design of the network that you're putting together for this?
And in this particular architecture, that is really a relevant point. And the reason it's a relevant point is because the back end firewalls sit in between the WAN links, right? And this is a discussion that I've had as well in this particular environment. So if this WAN link, if this WAN fails in any type of scenario, and running out of colours, so I'll need to go back to this one. But let's say like the traffic was initially coming round this way to get to an application here. Yeah, if that fails, routing will no longer be valid that way. But if it comes in this way and over here, that's great from a routing perspective. But what about this guy? He knows nothing about the session unless you've got like a clustered firewall between here. So you need to make sure that the application can tolerate that convergence, or you know, like you say, like you need, this is a business requirement. You have to say, like, if you're using SAP, I'm not picking on SAP, but I'm saying if you use SAP in data center 2 and the single router in data center 2 fails, unless you, well, you've got two options. You can deal with the TCP reset or whatever, and wait a few seconds, or potentially have to get the administrator to go in and kill the TCP session in the firewall in order for the whole of the network to be able to access that app via data center 1. So you do have redundancy, but there's a trade-off there. Or you can invest in a circuit, and that's what I was talking about. You might have, like, it might be load sharing or it might be load failover, so you ensure that you force traffic down, you know, via that firewall. In this scenario, what we actually looked at, and it was a compromise, was that I won't go into the detail, but like we used Lisp in order to say, you know, that host route, so that application server is no longer available out via DC2's WAN link. As soon as it disappears, the host route is available, but then you've still got the firewall question, because unless those are clustered across site,
So this is talking about whether you have to stretch layer 2 between the two data centers to accommodate the clustering, or to do the server. You know, if you're using VMware and vMotion between the two locations, all of those things need to be taken into account, right? And that's really, really important, that you don't do this stuff in isolation. It is essential what it comes back to, right?
And that's where you can get into like the vendor discussion. So you could say, right, like for example, I think the Cisco Firepower 4K firewalls, they I don't know if it's out yet, but I think they can cluster up to, I don't know whether it's across a layer 3 link or it has to be a layer 2 link, but they can, let's say for example, let's forget Cisco or whatever, let's say vendor 1 can cluster in some sort of way across site, so the policy and the state is synchronized without layer 2, versus vendor 2, which can only do it if layer 2 comes in. So then you say, well, do I go with traditional layer 2? Do I go with trunking? Do I go with L2 VPN? Do I go with OTV? And each of those all bring their challenges, right?
Exactly.
They've all got pros and cons, and that's where, you know, why, you know, to continue this discussion into the feature detail, you could do like a session on layer 2 DCI versus layer 3 DCI. But these are the types of things, again, coming up to the architect level, that you need to be aware of when you're designing a DC. And this is why it takes such a long time to design these types of projects.
Because everyone is while the sort of generic elements are there, all the things that we've talked about so far today and the others left, they'll still need to be there whatever you're doing. But the detail of how traffic flows through them is going to be dependent on what the applications are that are deployed in there. That's as simple as that. There's another example I've just thought there where you may have an application that needs a load balancer in front of it, or some global load balancing using DNS. And again, there's another set of requirements that places on the thing, right? So because that can be built into your failover scenarios, and your failover can be based on using the load balancers to achieve that. But they also bring their own complications as well. So similar, I guess, to the firewall in that sense, that you've got to maintain some state in there, and you've got to be able to share that state with across a cluster or whatever. So yeah, all very important.
And where the load balancer would, like, so there's two. That's a really good point. So the server load balancer, so that's like if you've got multiple servers. Some people will be experienced watching this, but some people will be learning. So the load balancer is you get SLB, so server load balancer. That would be like in a single DC, where you might have like 4 servers in a for one application, and you want to distribute the load within that DC. And then you might have like those 4 servers might synchronize to data center 2, where there's a load balancer there, but that doesn't actually kick in unless all of the 4 servers in data center 1 are unavailable. And this is where you say, well, if all the 4 servers for that app are unavailable, how do you do that? And that's where a global server load balancer sits at the next level above. So that like will probe the global server load balancer will probe like a virtual IP address which operates on behalf of all of the servers that are being load balanced by the SLB. And if all 4 of those are unavailable, the virtual IP will be unavailable, and then the global server load balancer will say, right, go over to the virtual IP at data center 2. So yeah, that's getting a bit like
it's detailed, but you're right. I mean, the point is some applications can be load balanced and others can't. Some applications, the failover will work well in that scenario and others won't. So it fundamentally it just comes back to that whole thing of understanding where the way your application functions and the failover that it needs to make it happen. I mean, there's all sorts of other things that we can talk about that we've kind of discussed some of that in the availability recording we did a few weeks back. Go have a look at that, because there are some interesting capabilities in there that play straight into these scenarios. So.
And then it's not, again, we could do like another episode on internet edge. So I don't want to downplay the internet edge, but I'm conscious that we don't want this video to be like too long. So to finish it off, like to the left of the data center 1 front end firewall. So what does a front end firewall do? It's basically the security people will tell me I'm wrong, and I am, I guess, because it's no longer the front door to your organization. Historically, the internet edge and the perimeter firewalls were the ingress egress points of your network, because that was the places that the internet's connected. But now everyone watching this video knows that that's not necessarily true. We have lots of like mobile users. They're effectively all exposed to the internet edge. So everywhere there's a laptop from your organization that's on the internet, that's where your internet edge goes to. We're looking at like split tunneling more now. It's been around for a long time, but with SD-WAN and hybrid transport, so an MPLS plus internet transport, we're now starting to see organizations say, I don't want to just like have that as a backup, like the MPLS and the internet going back to my data center and then breaking out to the internet or to the cloud, or like if they've got something in AWS, Azure, Google. They're saying like, we want to be able to break out from the site over the internet link, and this links into the last video that we talked about using NFV. So in order to scale that perimeter, the internet perimeter out from what you see in this diagram with the front end firewall, it goes out to the site now. But this is what we were talking about. You would want exactly the same firewall policy, more or less, or the same security policy as underpinned by the ISO organization or whatever that operates on the perimeter firewall in the data center out at the edge.
Yeah. I suppose the point here, what we're talking about here, is security in the data center.
Exactly.
Right. So which is still completely valid. compared to the scenario where, yes, if you're securing, once upon a time, the only way into a network for your organization from the internet would have been through your data centers. And what we're saying is, well, yes, it's not that anymore, but you still have to secure your data center. So this is still completely valid from that perspective, that you have your internet connections coming into there, into a pair of routers into the DCs, and then presenting themselves on the outside of firewalls allow you to do that initial screening, right, of and prevention of malicious traffic coming in into your DC.
Yeah. And just a couple of points then to finish off then. So this is a very simplified look at the internet edge. So the left of DC1 and the right of DC2 of the firewalls, that's the DMZ services. What could a DMZ service be? It could be like a proxy server. It could be where you put your VPN termination devices. It could be an e-commerce environment where you host your web servers.
Yeah, I was just thinking it could be a load balancer, right, for any inbound traffic from the internet for services presented out to the internet.
Yeah, so let's say for example there was some server down in the server farm that was presented out to the internet. Then that chain that we talked about, where you've got the global server load balancer that would sit in that DMZ services cloud somewhere, or it could sit on the outside of the firewall as well. There's different deployment models, but that would basically probe down into like the server farm infrastructure, and yeah, there would be components between the global server load balancer and the server. Like there'd be another load balancer that obviously has to go through a firewall. But what it's basically saying is, are you there in this data center? If it's not, then DNS gets updated to say go to data center 2. So that could sit like somewhere in and around the internet perimeter. So that's a good point on global server load balancing. Yeah. What else? And it could be like an active standby failover, or it could perform load balancing. So if you had an active service, web-facing service, the global server load balancer could also say go to the closest data center, and then even if one of them, if data center 1 fails over, send everything to data center 2, or vice versa for data center 2. What else happens at the internet edge on that internet edge firewall? So that's I just circle them in black. These ones here that we're talking about, they also still perform the traditional stuff. So on the outside of that firewall, between that iNet CE router and the outside interface of that firewall, that's where your network address translation will happen. So that can be anything from a single IP address for an organization, for a small company, to like it could be like a huge, like it could be like a /16. Do you know what I mean? Like it could, well, it's not going to be a /16, but you get what I mean, a /24, /23. Or it could be a small subnet like a /27, but you could advertise. We talked about this in one of the earlier videos, where you could advertise a /16 of PI space out. Maybe not from the firewall. I've seen some firewall designs where they've run BGP on the firewall and things like that. But all these different things, and that's recommended against by most people, but I've seen it done. So what else? Firewall. The firewall itself could terminate the VPNs, SSL, IPsec, VPN,
and VPN into cloud services and that sort of stuff. Yeah.
Yeah, and that CE router, yeah, that's basically peering with the ISP. So that could be a static route, or it could be via BGP, and it could receive, even if it's with BGP, it could receive the default, a partial routing table, or a full internet routing table. And yeah, and that's typically your gateway into the data center. But I mean, services coming into the data center are normally to consume applications, connect to VPNs at a very high level summary. And I think for today's episode, I think that's probably enough, and we can take some feedback, because this is a lot of stuff. Even though it's a small picture, this is like high level design, architectural design.
Yeah.
We talked about a fair amount of stuff, but this is where our episodes always run over, because every time we go into, like, the data center part, I want to talk in detail about that. Or if we could go into the DMZ and talk about that for hours, and
Yeah.
how each of those components. So really what we wanted to do is just set the scene for like a traditional, how a typical data center would look. And then, once this foundation is in place and this design is in place, you can then start running, for example, in the spine leaf architecture, you can run like ACI or Cumulus or whatever software defined data center, and use the fancy tools to orchestrate it, and APIs, etc.
I think that's it. It's like you say. This really illustrates quite neatly the layers in terms of the untrusted, semi-trusted, trusted networks. How those pieces bolt together, and then what we will do is in subsequent videos we'll drill down into some of these things to look at some of the technologies that are deployed in those environments to really show why you choose one over another, perhaps, and where the application that you're deploying kind of leads you in that direction. So yeah.
Yeah.
No, that's great stuff, mate. You happy with that?
Yeah, absolutely. I was just going to say, there's a fair point about let me see if this is working, my thing. Sorry about the technical issues. We'll try and get these sorted out for the next time. But just to kind of put this to bed, I mentioned it at the start, and I mentioned it in the slides. So this is untrust. If my PC reacts. But basically, the top of the infrastructure, where the front end firewalls are located. This will come back in a minute, or will it? No, it won't. Let me try and get it back up. Hopefully it's saved. Yeah. The top of the infrastructure, where the firewalls, the perimeter firewalls in the DMZ were located, that's the untrusted zone. Oh wow, that's different. Yeah, I think it's just loading.
Yeah.
Yeah. This is when you can tell it's a freestyle. Yeah. Hopefully you can see. Zoom out a little bit more. Yeah.
Yeah, we got it.
I'll try one more time and hopefully it doesn't crash. So what I'll do is I'll put forget this line at the top, but basically this is the untrusted. This is it's going to crash again. The WAN zone in the middle is the semi-trusted, and
Yeah.
below the back end firewall is the trusted zone.
Yeah.
So if I just put a T there, a U or an S there.
Yeah, that's cool.
You get the picture. So the untrusted zone, just now that there's some sort of indication, the untrusted zone is the front end firewalls, the middle part of the network where the wide area network connectivity is semi-trusted, because it's a private network, but it connects to like a public service provider cloud, and it could, like a WAN edge block now, could have internet connections in it, so that's why it would be firewalled off.
I guess as well, if there's any third-party connectivity to other organisations, you bring that in at the same place, right?
Yeah, or you could bring it in via the DMZ in the untrusted zone. It just depends on the architecture
Depends on the level of trust, I guess. Yeah.
Yeah, and then anything below the back end firewall within the data center is the trusted zone, and that kind of rounds it off, I think.
Well, thanks for walking us through that, mate. I think it was really useful to break it down in that way. And like I say, we'll hopefully go into some more detailed ones in some of those areas, particularly around the data center fabric and stuff. I think we covered pretty much all your points there. As usual, people who are watching, thank you for sitting with it and working with us on this one. Any comments or corrections or criticisms, always welcome, and you can contact us at NetFreestyle on Twitter or email networkfreestylers@gmail.com, or leave comments on the YouTube channel or on the blog at networkfreestyle.tech. Look forward again to hearing what you have to say. So thank you for watching.
Thanks, everyone. Goodbye.
Cheers.